My name is Stephen Hicks and I'm based at Imperial College London. I'm going to describe our novel approach in which we try to understand some of the broad industrial and geological factors that may correlate with and may therefore contribute to a recent emergent zone of seismicity in the Permian Basin in West Texas. And I'm pleased to say that our work has just been published in JGR. We know that many different industrial activities can cause earthquakes, and when these are large enough in magnitude, they can pose a significant hazard. But we also need to consider the pre-existing geological conditions that help to promote seismogenic failure along faults. Most studies that try to understand human-induced seismicity focus on numerical modelling of stress changes, such as those resulting from pore pressure and poroelastic effects. But these studies tend to focus on small regions, and they do not always explain why some areas remain largely aseismic. It is particularly challenging to answer these questions for large regions and where many different industrial activities may be at play rather than just one or two types. One such region is the Permian Basin in West Texas. This is a region of intense industrial activity, and within our area of interest there are over 500,000 wells in our database that has been provided by IHS Markit. In fact, if we zoom in on a smaller region in southern New Mexico here, as shown by the red box, you can see a very high density of wells within just a 30 by 30 kilometre area. And if you haven't done so already, I highly recommend having a look at satellite images in this area, like this one below, to truly comprehend the scale of subsurface industrial activity here. Geologically, it's an interesting area because there are a number of mapped near-tectonic faults, as shown by the blue lines, to the west of the Delaware Basin, which is where most seismicity has emerged since 2017, as shown by the red circles. There are multiple ongoing clusters of seismicity in the area, and the largest earthquake had a magnitude of nearly 5, which occurred in the Mentone area in 2020. However, the causative factors driving this seismicity remain debated due to the different types of industrial activities in the region. These maps show some of the different industrial activities going on, in which each triangle corresponds to a single well. So for many decades, oil and gas has been extracted using fairly conventional means from the shallower parts of the basin, such as the Delaware Mountain Group. And intense hydraulic fracturing operations over the past decade are targeting the Wolfcamp shales. And there has also been high-volume saltwater disposal into the deeper parts of the basin, such as the Ellenberg Group. But more prevalent is wastewater injection at shallower depths into the oil and gas reservoirs that were previously produced from. Nevertheless, by comparing the seismicity, as shown by the red circles, with these well activities, it is clear that there is no obvious single correlation between any one industrial activity type and earthquake occurrence. Therefore, we need to account for the interplay between multiple factors when determining some of the causative mechanisms that might be driving seismicity in this area. The approach that we have taken to try and model seismicity in the Permian Basin is to use logistic regression, which is a fairly common data science method and often forms the basis of machine learning algorithms. We take input features, which in this case are a range of spatially varying industrial and geological parameters, to try and hindcast or retrospectively forecast earthquake occurrence, which is our target variable. And this is represented by a binary classification scheme. The relative coefficients of the scaled features in the logistic model represents their importance in correlating with seismicity. This approach allows us, therefore, to model the complex interplay between multiple factors in determining seismicity. So here is our target variable. We use a 2D spatial grid with 5 km spacing and classify where the grid points contain at least one earthquake above a completeness magnitude of 2.2. This binary classification scheme is advantageous because it means we do not need to worry about declustering the catalogue, nor do we need to consider variable hypocentral depths, which remain highly uncertain across West Texas. As you can see, the grid accurately represents the main seismicity clusters in the area, including those in the Pecos area, that in Culberson County, and the Odessa cluster in the Midland Basin to the east. Now let's look at some of the industrial parameters that we input into our logistic regression model. We use all possible types of fluid extraction and ejection data to determine the volumetric sums from wells within a given distance of each grid point. We use 3 kernels of 5, 10 and 25 km radial distance to try and represent both near-field pore pressure effects, such as those expected from hydraulic fracturing, along with the possibility of longer wavelength triggering from poroelastic stress changes that might occur due to, for example, high volume wastewater disposal from multiple wells. And here are 3 examples of industrial activity types. Hydraulic fracturing, and both shallow and deep near basement wastewater disposal. Their absolute values are shown in the left-hand column, But because injection and extraction volumes within several years from wells may differ in many orders of magnitude, we need to scale and standardize these features so we can interpret their relative importances in the logistic model. These scaled features are shown in the central column, and if we try model earthquake occurrence with each feature individually, you can see from the right-hand column that any correlations are very weak, although you can see slight positive relationships with hydraulic fracturing and shallow saltwater disposal. So now let's look at what happens when we combine multiple industrial activities into a single logistic regression model. In the top panel on the left is the actual distribution of earthquake occurrence, and the central panel shows the prediction from the logistic regression model, with the residual between the model and data shown on the right. As you can see, the model roughly reproduces the main locus of seismicity in the Delaware Basin, but certain parts remain underpredicted, particularly at the edges of the PCOS cluster. The pseudo R-squared score of 0.29, representing the model fit, it indicates an adequate performance of the model, but maybe we can do better. The chart in panel B shows the relative normalized importances of the different industrial activities in the model. And it's worth noting that initially the largest positive contributions come from shallow saltwater disposal and to a slightly lesser extent from hydraulic fracturing. So as well as just industrial parameters, we add in some geological features that help to model the spatial distribution of seismicity. Perhaps the most first order feature is depth to basement across the Permian Basin. This is shown in the top left panel. And basement depth has been shown to increase the propensity of induced seismicity in Oklahoma. There are significant changes in basin structure across the area. From the west, the Delaware Basin gradually deepens before a sharp basement high is encountered, corresponding to the central basin platform. Going east, there is a further deepening in the Midland Basin. As shown by focal mechanisms and well breakout data, there is a predominant normal faulting stress regime in the area. This is shown by the second panel that shows relative stress magnitudes in terms of the A phi parameter. This means we can use an interpolated field of SH max azimuths from Lund, Snee and Sobach, as shown by the third panel, and combine these with fault orientations to define a metric of their angular difference. This angular difference between SH max and fault strike is a simple proxy for the degree to which faults are oriented for failure in this extensional stress field. Several mapped fault datasets are available, as shown in the lower three panels, and these are largely interpreted from stratigraphic thickness changes across the basin. We use the recent basement-rooted fault dataset from Horn et al., along with coarser legacy datasets of faults within the basement itself. Finally, due to evidence for recently active faults to the west of the Delaware Basin, we design a feature that represents the proximity to these Quaternary faults, which is a rough proxy for pre-existing tectonic stress levels. And here is our hybrid logistic regression model using both industrial and geological features. Compared to the model that uses industrial data only, the hybrid approach does a much better job of reproducing the seismicity in PCOS, Reeves, and Culberson counties. This improvement is also shown by the R-squared value, which increases by 28% from the industrial-only model. And these main features of the modelled earthquake occurrence are also robust at 95% confidence based on the model's standard errors. Now let's have a look at the most important features of the model. The red bars here show the coefficients of the optimum result, and the blue histograms indicate the uncertainties in these model coefficients based on bootstrap resampling of model grid points. The narrow range of these blue curves shows that we are not overfitting the data. In order of their importance, the five most significant features are proximity to Quaternary faults, injection into shallow formations in the basin such as the Delaware Mountain Group, hydraulic fracturing, deep saltwater disposal, which interestingly has a negative coefficient, and the optimal orientation of basement-rooted faults. Now let's discuss the implications of each of these. Proximity to Quaternary faults is the most important factor in our model, so we therefore interpret that higher pre-existing tectonic stress levels to the west of the Delaware Basin increase the likelihood of induced seismicity. The role of these faults in indicated regional pre-existing stress has not yet been identified in the rapidly growing set of studies on induced seismicity in the region. The significance of these faults also offers a key contrast with the well-studied induced seismicity in Oklahoma, where there is no such near-tectonic faulting. The significance of wastewater injection into shallow formations such as the Delaware Mountain Group has also been recognised in a couple of studies that have been published in the last year or so. In our model, this feature has an optimum radial distance of 10 to 25 kilometres, which could indicate a role of longer wavelength poroelastic stress transfer. The role of shallow injection seems to be consistent with the slip tendency of newly mapped shallow, non-basement rooted normal faults as reported in the recent study of Hennings et al. This study shows that these shallow faults are more optimally oriented for failure than the basement rooted faults. However, key questions still remain over whether the hypercentral depths in the region can actually physically support such slip at shallow depths, or whether a more complex depth-dependent triggering mechanism should be considered. Hydraulic fracturing plays a more secondary role to shallow wastewater disposal, and its smaller coefficient indicates that it is likely more of a localized rather than regionally prevalent feature. Deep saltwater disposal over large radial distances has a negative coefficient in our model, which indicates that somehow it anti-correlates with seismicity. You can see this from the plot of deep wastewater disposal volumes, that you would need the highest volume disposal wells up in New Mexico to have an even larger regional footprint of more than 25 kilometers to correlate with the seismicity in the western part of Culberson County. However, some studies have attributed deep saltwater disposal to triggering the magnitude 5 Mentone earthquake. So perhaps deep injection plays a highly localized role. Possibly the prevalence of deep disposal wells in the Central Basin platform, where there is virtually no seismicity, contributes to the negative coefficient in our model. Finally, the optimal orientation of basement-rooted faults plays a small role in our model. This result probably arises because these deep faults are oriented subparallel to the main lineations in seismicity, particularly in Pecos County. Future work to incorporate the recent shallow normal fault dataset of Hennings et al. Could result in these faults playing a more significant role in a future logistic regression model. Finally, before I conclude my presentation, it is important to be aware of the areas in which our logistic model underpredicts seismicity. These are shown by the blue areas in the residual plot. First of all, the westernmost part of the seismicity cluster in Culberson County is not reproduced. This suggests that other unmodelled factors may contribute to the seismicity here, which lies several tens of kilometres from the nearest high-volume disposal wells. Seismicity here might be due to either a very high localised diffusivity value, which may allow longer distance coupled pore pressure and poroelastic effects, or earthquake-to-earthquake triggering interactions that may be sustaining the swarm-like nature of this cluster. Second, seismicity along the New Mexico-Texas border area is significantly underpredicted. Maybe this is localised triggering from deep saltwater disposal, since this cluster is close to the highest volume deep disposal wells. Finally, we are not able to fit the Odessa cluster to the east, which might also be due to deep near basement injection activities. In this case, then, the state border and Odessa clusters would be inconsistent with the overall negative coefficient of deep injection in our model. So, to conclude, a combination of industrial and geological factors are needed to accurately model the spatial distribution of seismicity in the Permian Basin. For the first time, we have shown the possible role of pre-existing stress states in the area, as evidenced by neotectonic faulting. Our results show that shallow wastewater injection is likely the most important industrial factor in causing seismicity in the Permian Basin, with more minor localized roles from hydraulic fracturing and possibly deep injection. And our logistic regression approach offers an efficient way to test hypotheses of factors that contribute to induced seismicity, and it is highly adaptable to new datasets as they become available. And for more details, please take a look at our newly published paper in JGR. Thank you so much for listening.